quick announcement. I'm going to use laser pointer. Just a second. And I'm going to use this screen. So those people sitting here, please move either to the center rows or to the right side. You prefer to stay there? Okay. Well, I think it depends on how close I am to the mic rather than those. Okay. Okay, so let's start. Thank you for coming for my talk. It's the first talk in the morning, so it might be pretty difficult for you to get up early and come here. So thank you for showing up. The title of my talk is DIRA, which is a tool for automatic detection, identification, and repair of control hijacking attacks. I'm Alexey Smirnov, and this is a joint work with Chiueh, who's my advisor. We are from Stony Brook University. Here's the outline of my talk. First, I'm going to give a brief introduction on control hijacking attacks. Then I'm going to talk about the related work in the areas of attack detection, identification, and repair. Then I'll present our architecture, DIRA, which has these three components: the attack detection component, the attack identification, and attack repair component. The purpose of attack detection component is to detect a buffer overflow or a control hijacking attack. So it's similar to the goal of the tools like Tzi-cker and propagation. The attack identification component builds up the signature that can be supplied to intrusion detection system so that these attack packets can be filtered out in the future. The attack repair component repairs the program and allows it to continue its execution as if the attack never happened. In the performance evaluation part, we're going to talk about the overheads, the runtime overhead, and the compile time overheads of our compiler. And we'll conclude with the summary of research contributions and with the directions for future work. Buffer overflow attacks are the most common type of attacks. Computer worms use buffer overflow attacks as a basic building block for the propagation. So as soon as they arrive to a new host, they perform a buffer overflow attack, hijack control of the underlying program or of the host, and then scan for more vulnerable machines by performing random IP scanning. Once they find a new vulnerable machine, they send their body to the new machine and perform the control hijacking attack on that new host. A comprehensive protection strategy should include the following three components. The attack detection component, which will detect the control hijacking attack when it happens. That is, when the worm tries to get control of the underlying computer. The attack identification component is responsible for building the signature of the attack. That is, for identifying malicious packets and representing them in the most general form so that polymorphic worms or polymorphic attacks can be detected by the same signature. The attack repair component allows the compromised program to continue its execution as if the attack never happened. That is, it should restore the memory, image, or the environment of the program as it was in the pre-attack time, so that the program will think that it has never received any attack packets. We propose a compiler. DIRA is a compiler that instruments programs, source code of a program, so that the instrumental program can identify, detect, and repair itself after a control hijacking attack. What is a buffer overflow attack? Well, the idea behind control hijacking attacks is to overwrite a control-sensitive data structure, such as a return address, function pointer, or any other control-sensitive data structure. By the way, I've got some T-shirts here and books, and I'm going to give them away, and I'm going to ask you questions and who answers first gets a t-shirt or a book. So here's the first question. The return address and the function pointer are two possible types of control-sensitive data structure. What are other data structures that a worm or a virus can override? That's what I said, function pointer. What else? Okay. What on heap? What do you mean by heap? Well, okay, you got a t-shirt. Okay, please pass it to him. What else? That's what he said, probably heap. Okay, that was what I. So the name of the control-sensitive data structure is just word. Okay, any other ideas? Okay. Well, for example, GOT, which is global offsets table. Anyway, buffer overflows are possible when the length of the destination buffer is shorter than the length of the data that's been written into it. So whenever you write something that is longer, it can overwrite something that is behind this buffer, such as a return address. And that's when the buffer overflow happens. Standard libc functions, such as string cpy or sprintf, are responsible for most buffer overflow attacks. So we're going to review related work in the areas of attack detection, identification, and repair. Stack guard is the first tool for buffer overflow attack detection. It works by placing a canary bird in the stack frame and in the function prologue, and then check this canary bird at function epilogue. If the values are different, then the attack has happened and the application is terminated. RAD is another tool that protects programs for buffer overflow attacks. It works by saving the original return address in a special well-protected buffer at function prologue and compares it with the values stored in the stack at function epilogue. If the value is stored in the protected buffer and in the buffer in the function frame, when the function returns are different, then an attack is detected. Can anyone think of any other tools for attack detection? Now, Snore is content filter engine. Okay, I got it. You got a t-shirt? Who was that? Sorry. So let's move to attack identification. We need automatic ways for attack identification because it's very important to generate signatures fast. Computer worms infect vulnerable machines very fast. At rate of 1,000 per minute, or maybe tens of thousands per minute. Therefore, if we wait for a human expert to come up with a signature, which is going to take a few hours, then the worm is going to hijack most vulnerable hosts on the internet. Recent epidemics propagated at a very, very high speed, so it's very difficult for human expert to come up with a signature quickly. Previous systems for automatic signature generation either produce signatures that consist of only one packet or required a large pool of malicious network data to come up with a comprehensive signature. Signature that consists of one packet is sometimes insufficient because a complex attack can involve multiple packets, such as, let's say, FTP server attack. It involves sending out authentication packets and only then sending out the final attack packet. A comprehensive signature should include all attack packets, not just the last one. So here are some relevant projects. Taint-check is a tool for, it uses the taint analysis to generate attack signature, and it reports the value of the return address that worm used to hijack control as its signature. So it's only a 4-byte signature. Autograph uses so-called Arabian fingerprints to find common subsequences in a large pool of malicious network data. Polygraph and Neiman also use large pool of malicious data and to use machine learning algorithms to construct a multi-packet signature. Attack repair relies on checkpointing. That is, one first checkpoints the program state and then jumps to a previous point in the past to restore program's execution. So two approaches here are either keeping complete execution history or do periodic stacked checkpointing. That is to take a snapshot of the memory image of the program. And the second approach relies on a fork system call, which is available under Linux, but might not be available under other operating systems. And Shadow Honeypot project runs two versions of the application, instrumented, that is protected and non-protected, and switch between them dynamically when it detects an attack. Now we move on to DIRA architecture. DIRA is a compiler that provides all these three components: attack detection component, attack identification, and attack repair component. As I said, DIRA is an extension to GCC, version 3.4.1 currently, but it can be used with other versions as well. The idea behind DIRA is memory updates logging, and this approach solves all these three problems at the same time. So the idea is to maintain a runtime log of all changes that the program performs. Assignments such as A equals B or libc functions call such as memcpy change memory state of the program, and therefore their effects should be saved. For example, okay, we will see some examples later. For each memory update, DIRA stores its source address, its destination address, its length, and the pre-image. So in the case of the assignment, A equals B. Where's my pointer? Here. The source is the address of variable B, because that's where the new data comes from. The write address is the address of A, because that's the address where the data is being written into. The length of the data is the size of type of variable B. So if it's integer, it's 4 bytes. The preimage is the old value of A, and it's used to restore memory image to the program. So the DIRA compiler instruments the source code of the program in compile time. It adds the logging code for variable assignment and for standard library functions. At runtime, this logging code, this memory update log is generated, and it's used at repair time to detect, to identify, and to repair the attack. So how can we detect, identify, and repair an attack if we have this memory update log? To detect an attack, we need to compare the current value of the return pointer or the return address saved in the stack frame with the value saved in the memory update log. When we invoke a function, we lay out a new stack frame, we save the old return address, we save any registers that are used in this function, and therefore this is a change to the memory state of the program, which should be saved in the memory update log according to our concept. Therefore, the old value of the return address will be saved in the memory update log when the function is invoked. When the function is returning, this saved value should be compared with the value that is currently on the stack. If these two values are different, then there is an attack. To identify an attack using memory update log, we can trace back the data that overrode the control sensitive data structure to the point where it was first received in the program. For example, through a receive call. To repair an attack, we need to restore the memory image of the program by using the pre-images that are also saved in the memory update log. So this idea of keeping the memory update log of program memory state changes is the essential idea behind our tool. And it allows us to solve all these three problems of attack detection, identification, and repair in the same uniform way. Memory update log is a circle buffer. Each record of this buffer has 4 fields: read address, write address, length, and data. DIRA saves the effect of each operation, of each assignment operation, and such as x equals y, where x and y are either directly referenced variables, array references, or dereferenced variables. As I said previously, the read address is set to the address of the right-hand side, the write address is set to the address of the left-hand side, the length is set to the size of the memory update, and the data is set to the preimage that stores the data that we're going to overwrite. That is the old value of x. If the right-hand side is a complex expression, then a log record is created for each variable in the right-hand side. To handle memory change performed by standard library functions, DIRA proxies a few of them. such as string manipulation functions, format string functions, file network I/O functions, and other functions that change memory state of the program. So the proxy function constructs a new memory update log record that summarizes the changes performed by the corresponding libc function. And the memory update log is also used to store tags, which are special records that indicate change to memory to the state of the program. For example, when the function is invoked, function enter tag is inserted, and when the function returns, function exit tag is inserted. These tags are used at repair and identification time to build up signature and to repair program after an attack. So here are a few examples. At compile time, let's say there is a statement x equals y plus z. So the instrumental code, the compiler adds two logging calls. The first call logs the effect of variable y, of variable z, the other of the variable y. And finally, there is this original statement. At runtime, these two logging calls produce these two log records with the read and write addresses set as I described previously. Suppose there is the string CPY code in the source code of the program. The DIRA compiler replaces this code with a proxy function. And at runtime, this proxy function inserts a log record with the read address of B, because that's where the data is coming from, with the write address of A, because that's where we write data into, with the length strlen of B plus 1, because they're going to write strlen of B bytes plus not terminating character, and with the preimage is A, which is the old value of A, the variable, the buffer that we replace. Now let's talk about attack detection. DIRA uses ReadWrite approach. That is, it saves the original return address when the function is invoked. It compares the saved value with the value that is currently on stack at function epilogue. If these two values are different, then an attack is detected. DIRA can protect other control-sensitive data structures, such as function pointers, GOT, signal handle tables, in a similar function, but it's not implemented yet. Now let's talk about attack identification. So here are the desired properties of an ideal signature. A signature should be context-aware, which means that it should include all the attack packets that participate in a given attack. And this allows to reduce the rate of false positives. It should be also semantics-aware, that it ideally should incorporate the knowledge about the protocol. For example, if this is an HTTP attack and the attack request is a GET request, then the signature should specify that this is GET, so that the intrusion detection system can filter out or can just keep all the requests of other types, of other protocols, and if it's HTTP but not GET, it should also discard those packets. It should check the signature only against packets that are HTTP GET kind of packets. And this also allows to reduce the rate of false positives. And the signature should provide a certain degree of flexibility within each packet, so that polymorphic forms that change their body as they propagate can be matched using the same signature. The attack packets should be represented as regular expressions, and that's the desired flexibility that a signature should have. So as I said, these three properties are the desired properties, and now let's see how DIRA satisfies all those properties. DIRA signatures are context-aware because they consist of multiple packets. They consist of all packets that an attack consists of. And each of those packets is represented as a regular expression. And there's a feature called length constraint that allows to limit the attacking part of the packet. That is, it allows to specify that a terminating character, such as null character, should occur between offset like A and offset B. If the terminating sequence occurs within this offset, this is not an attack packet. If there is no such a terminating character in the packet, then this is the attack packet. So in some sense, this is equivalent to semantics awareness, because it allows to narrow down the part of the packet that the intrusion detection system searches. So it doesn't search the specified sequence in the whole packet, but rather this length constraint allows to limit or to narrow down the scope where we search for the required terminating constraint. For example, if this is a same example, if it's a GET attack and there's an overly long URL which is terminated by a null character, DIRA allows to specify that this null character should occur between the 4th and, let's say, 20th byte of the packet, because the first 3 characters are the get characters, and then the remaining part of the packet is the URL. If the terminating character is found in the first 24 bytes of the packet, then this is not an attacking packet. If the now terminating character is not found in the first 24 bytes, then this is an attack packet because the URL is too long. Memory updates log allows us to construct signatures that consist of multiple packets, to represent each packet as a regular expression, and to generate a length constraint. And we're going to give an example, and we will show how all this functionality is implemented. 2 types of dependencies exist in the program: data and control dependency. Data dependency is created when one variable is assigned to another. For example, A equals B, same example. In this case, A depends on B. A control dependency is created whenever variable X and let's say variable Y is used. Variable X is used in conditional expressions such as if, and Y is in this conditional body. So here's an example. In this case, even though there is no direct assignment between X and Y, Y depends on X because the value that Y will take depends on the value of X. This type of dependency is called control dependency. No direct assignment, but dependency is there because value of Y depends on value of X. Why we need control dependencies? So here's an example: FTP server attack involving authentication. Here's an example of vulnerable FTP server. So here's the vulnerable buffer. The program has 2 state variables: is authentication, is user. And here's the main loop of this server. First, it receives the packet. Then it compares the 4 bytes of the packet. If it's quick command, the loop breaks. If it's user command, then is user variable is set to 1. If it's password command, then is user has been set. Then authentication has been completed, and is authenticated variable set to 1. If authentication was not performed previously, then the program continues. The client requests are handled only in the case when if the authentication has been completed previously. So if the user is authenticated, then the program checks the first 3 bytes of the packet. If it's get packet, then there's a get request, and it returns the file that the user requested. But this request is only processed if the user has previously authenticated. So these are the 3 packets used in the attack. There is a URL. There is a file name that is too long and that overrides the buffer. That overrides this buffer, which is only 16 bytes long. Let's look at log records generated at runtime. First, there is a log record DIRA receive for the receive function, for the proxy function, proxy standard receive call, and it has this tag. Here's the tag. This is the write address. That's the destination where the network data is written into 11 init length, and here's also the image of the data that we read from network. Then there's a proxy function for str and CMP, which also has the write address. It's read address of the variable. 4 is the length of the argument. So this record specifies, indicates that we search buffer P, and we look at first 4 bytes of this buffer. Then this record is created for conditional expression, and it means that variable P participates in the if expression. So for every variable in the if expression, we save this variable into memory updates log. And this is also the record for the statement that updates is user variable. So in this case, the read address is set to null because we don't know where the data that is written into is user comes from, and it's just a constant. So the write address is user, the length is 4, and is user is preimage. Similarly, for the second packet, we have the receive record here. We have the string comparison record that checks the first 4 bytes of the packet, we have two conditional variables now because two variables are checked, P and isUser. And finally, this is the record that updates the isAuthentication variable. So finally, let's look at the third packet. So we also have a record when the packet is received. Then we also have the conditional record for variable isAuthenticated. Then there is the record for string comparison that checks the first 3 bytes of the packet. Then there is the conditional record for P. And finally, this is the record that was created by string CPY proxy function. And it describes the fact that the data from buffer here, the data from buffer P+4 was written into buffer. And the length of the update is str length of P minus 4 plus 1, because all bytes of P except the first 4 bytes were copied into buffer buff. And we also save the pre-image of P. So this is the summary. These are all log records that are generated at runtime when this server attack is executed. And suppose that the return address is located after the buff variable. That is, the return address is saved at the offset buff plus 17. Buffer is a buffer of 16 bytes. So the return address is saved at the offset 17. Now let's see how we can detect the control hijacking attack using this memory updates log. So we start with log record, with the last log record that overrode this buffer. And here's its right address. So we look for the source of this data. That is, we try to find out where the data came from. And this log record allows us to conclude that this data came from P. Return address was saved at the offset buff plus 17. Therefore, the data was read from the offset P plus 4 plus 17, which is P plus 21. That is, the return address value came from memory address P plus 4 plus 17, which is P plus 21. So this is the new address that we look for. Now we search memory on this log for the address P plus 21. And if we traverse this log record, this memory of this log upward, we can find that there is this receive record that read data from network into buffer P, and the length was 62. And we'll look for memory location with the address P plus 21. And this is the record that is written data from network into that memory location. So we conclude that here is the read operation that read data from network and wrote it into address P plus 21. And because this is the operation that reads data from network, we conclude that this is the attacking packet. So this way we identify the first attacking packet. Is it the only packet in the attack? Probably not, because the user requests are only processed if the user has authenticated. So we need to continue our search and try to find more attacking packets. Sure. Well, debugging is not automatic. Our tool is completely automatic. It doesn't require any user involvement at all. So the process that I described here is completely automatic. It's performed by our program, not by the user, not manually. It's not log analysis performed by a human expert. It's log analysis performed automatically. Well, you are right. Well, that's the question of our performance evaluation. We'll get to this question later. And if I don't give a clear answer, I'd like to talk to you offline. So as I said previously, we were able to identify the first attacking packet, and now we look for more attacking packets. And here's where we use conditional dependencies. Let's look at the first memory update statement. If we go upward, we can see that this statement depends on two conditions. That is, it's inside two outer if statements. The first if statement checks p variable, and the second checks is authenticated variable. Therefore, this memory update was only possible because of these two checks that involve these two variables. Variable p has been found before, so this record should be discarded, whereas this variable is authenticated should be used for later search. So we continue with variable is authenticated, and we try to find out whether this variable depends on network packet or not. So if we continue traversing this log upward, we can see this memory updates log operation. And the read address of this operation is unknown because this variable was assigned to a constant. Therefore, we should again use condition dependencies to find out what our variable is authenticated depends on. And we can see two conditional log records, isUser and p here, which means that variable is authenticated depends conditionally on isUser and p. So we now look for p and isUser. We can find p here. Therefore, we conclude that variable isUser depends on network packet that contains password. And this turns out to be true because variable p is set only if the attacker sends password packet. But variable isUser also depends. Variable is authenticated also depends on isUser. So we continue with this variable isUser, and we can find it here. This is the memory update long operation that sets variable isUser. Its read address is also unknown because it's set to a constant. Therefore, we should again use control dependencies to find out whether variable isUser depends on any network packets. And once again, we can see this conditional expression that uses variable p. Therefore, we now search for variable p and try to find out whether it depends on any network data. And it turns out to be true. Variable p contains the packet payload of the user command. So what we can see now, we have found 3 attack packets. And so the get packet, pass packet, and user packet. The first packet was found using direct dependencies. The remaining 2 packets were found using control dependencies. So the control dependencies are really important to link the first attacking packet to all the remaining attacking packets because of these state variables that are used in network daemons. Sure. Sure. Well, this is just our assumption. Well, the real value of the return errors is returned by the attack detection component. Well, this is attack identification. The attack detection component tells you which data structure was damaged. So it tells you the address of the compromised data structure, which in our case is the return address. So this assumption, I just made it up. But this address is always known at runtime. No problem. Let's now give a precise definition of control dependencies. We say that whenever variable x can prevent control flow from reaching variable y, a control dependency is created between x and y. Let's look at these examples here. The left-hand side example shows an if condition. In this case, statement 1 and 2 depend on condition, but statements 3 to n do not depend on condition because they will be reached no matter what the value of variable count is. However, if you look at the right-hand side, then one of these branches here, this branch, has a return. And therefore, if condition takes such a value that this branch is taken, then the function will return and statements 3 to n will not be executed. Therefore, statements 3 to n depend conditionally on variable con. So whenever a variable, conditional variable, can prevent certain statements from executing, those statements become dependent on the conditional variable. Conditional dependencies can also be created for while and for loops as well. So we've talked about how to find all the attack packets. Now let's talk about how to represent the attack packets as regular expressions. For each byte of the attack packet, DIRA determines whether it was looked at or not non-looked at. That is, looked at bytes are those that are important to the program. That is, the bytes that the program makes control decision on, based on. Non-looked bytes are those that are not important to programs. That is, they can take any values. The bytes that were not looked at are represented as wildcards in the signature file because the program doesn't care about them. The looked at bytes are presented as they appear in the attacking signature, in the attacking packet. For example, string comparison function compares certain bytes of the packet with, let's say, control words such as get word or password or user keyword, and therefore bytes that match these keywords are important to the program. Because if those bytes of the packets were different, the program wouldn't proceed the way it actually proceeded, and the attack could not happen. DIRA traverses the log forward from where the packets were received to the end of the log and detects the bytes that were looked at by the program. And as I said previously, those bytes that were looked at are output as is, and non-looked bytes are output as question marks. So here's an example. That's our example once again. So here's the receive record. Here's the string comparison function that compares first 4 bytes of the network packet. Therefore, this keyword becomes important to the program. If this was not user, let's say if there was quit command, then the program exited. Therefore, these user bytes are important to the program. So we can conclude the same about password and get bytes. But let's look at the last record. Even though program manipulates records of the P buffer, those bytes are manipulated blindly. That the program doesn't make any control decisions based on the values of those bytes. Therefore, even though they were copied by the program, they were, we can say, touched by the program didn't make any control decisions based on those bytes. Therefore, they are not important to the program, and they can be dumped as question marks in the signature file. And here's the length constraint. So here's our network packet. And here's the stack. And this is the return address that was overwritten by the attack. And this is the memory update operation that overrode the return address. So the identification part of DIRA determines the extent of the stack frame that was overwritten by the attacker. And reconstructs the pre-image using this traceback procedure. It builds up the pre-image of this memory update in the network packet. So this big white dot is the pre-image of return address, and this is the terminating character. So that is the last character of the attacking part of the packet. In our case, it's now character. If we trace it back to the network packet, we can assume that this is a new line character. So the length constraint should specify that the terminating character should occur between the beginning of this gray area until the pre-image of the return address. If this terminating character occurred here, then the memory added operation wouldn't touch return address. It would stop earlier. However, since the terminating character was not found there, the control hijacking attack occurred. So the length constraint limits the attacking part of the packet, which is this gray part. By specifying the terminating character and the maximum offset, in our case, this is the pre-image of the return address, where this terminating character should occur. Here's the format of the DIRA signature file. First counts the number of packets, then the length of the current packet, then the regular expressions that represents the packet. And for the last attacking packet, we specify the length constraint that limits the length of the attacking part of the packet. Here's the signature for our example. We have 3 packets. Here's the length of the first packet, 11. This is the representation of the packet as a regular expression. The first 4 bytes are important to the program because the program used them in string comparison function. The rest of this packet is not important, and it's represented as question marks. The second packet has length 12, and it's represented as password followed by question marks. So once again, these bytes were analyzed by the program. The remaining part, it was used by the program blindly. The program didn't care about it. And here's the last packet. The length is 62. The packet is get, followed by question marks. Once again, get was analyzed by the program using string comparison function. The file name contained here was not analyzed. Even though program fetched file using this file name, or at least tried to fetch it, the bytes that build up this file name were not analyzed by the program. The program didn't make any control flow decisions based on those bytes. Therefore, these bytes are represented as question marks in the signature. They are not important. So any value in the user or pass packets will be good enough for the attacker. Of course, that's not true in practice because there are like authentication databases, password files, stuff like that. But for our example, it's the case that the byte that follow user, pass, and get commands are not important for our program. The length constraint specifies that starting from byte 4 to byte 17, there should be null character. If this null character is found, this is not an attacker packet. If this character is not found, then the return address is overwritten because it's stored at the offset 17. Now let's talk about attack recovery. Attack recovery brings the program to the state in which it was before the attack packets were received. So, sure. You are right. That's what we need proxy functions for. DIRA proxy functions take care of this kind of special cases. Proxy function creates memory updates log that summarizes the effects of the original libc function call. So two questions are involved with attack recovery. First, how to restore the pre-attack state. Second, from which point to execute to resume execution. The pre-attack state is restored by restoring memory updates, memory image of the program using the information stored in the memory updates log. These pre-images stored in the memory updates log. The restart point is found in the following way. We use the least common dynamic assessor of the function in which the attack was detected and the function in which the data was read in. And the following example illustrates why this is the proper function. So here's the function where the data was read in. Here's the function where the attack was detected. We can restart execution only from function f1. Why? Because the execution flow returned from function f3 to f2 to f1, then went to f4 and f5. And while it was in f1, it could change the local state of function f1. It could change its local variables. And I didn't tell you that we don't keep the memory state change, the effects of memory state change of local variables in this mode because it becomes too expensive. We record or we save the effect only of the global variable changes in this mode, in the mode when we support recovery. And therefore, if we change the local variables of function f1, we couldn't recover them, and we have to restart function f1 from the beginning. At the same time, function f0 was not changed. The control flow didn't go there when it traversed from f3 to f5. Therefore, the local state of function f0 is the same as it was before. Therefore, we can restart execution from function f1 here, which is the least common dynamic assessor of the function where the data was read in and the function where the attack occurred. And there's a memory address log, and there's an algorithm that allows one to find the least common dynamic assessor of the two functions, but I don't want to go into the details of this algorithm. So this slide summarizes the algorithm for finding the restart point. We don't use any specific operating system features for this, but we rather use long jump and send jump functions. Before each function call, we insert the send jump call, which saves the value of the stack pointer and allows us to continue the execution by performing long jump call using that buffer. So these set jump calls are set in front of each function invocation. Whenever we want to start execution from a specific function, we just perform long jump using that set jump point. Now we move to performance evaluation and hopefully. Well, this, DIRA proxy functions take care of this. They are responsible for saving any side effects of library calls or any other calls performed by the program. So for each socket read, let's say socket open, socket close, there should be a proxy function that summarizes the effect of this operation and saves it in memory on this log. And at the repair time, this log record will be processed by the repair procedure, and the repair procedure will undo the effect of the socket open, socket close. If it's socket open, then it will close. If it's socket closed, then it will reopen socket, so on. So this is why we need proxy functions. Okay, we had 5 programs, and for 3 of these programs we had exploits, which we downloaded from public exploit databases. Can anyone name any exploit databases? That's a question for a T-shirt or for Brook? Yes? What's that? Yes. Okay. You get this book. Any other exploit databases? Publicly available? Come on, you're hackers. Okay. What's that? Okay, book. Okay, one more hand there. Who is? Okay, excellent. Okay, what's your answer? Hexer? Packet Storm. Does it have exploits? It does? Okay. Book. One more? Excellent. Come here. Okay, it's security. Book. Okay. So our performance evaluation had 2 goals in mind. First, we wanted to find out the runtime overheads and the quality of automatically. The runtime overheads, the second goal was to find out the quality of automatically generated signatures. So in our configuration, we had server machines, we had a few client machines, and we used exploits from security team and from insecure.org, which are two publicly available sites that contain exploits. So here's the graphs that describe the performance overheads. So the performance overhead can be as high as 70%, which we think prevents our system from being deployed on client machines, but we think that our machine can be deployed as a honeypot, as a special dedicated server that runs the instrumented programs and catches all attack attempts. And on the right-hand side, you can see this is the percentage, the breakdown of the type of the log record that were saved in the memory on this log. These are the signatures that were generated for the 3 exploits that we had. So we had this HTTP attack. GHTTP is an HTTP server. The named is a DNS server, which is part of the bind program. And CatD is a remote cat daemon. So well, it's 70%. 70. So here are the programs. This is the, well, we compared the original non-instrumented program. We had several client requests, like benign client requests, and we ran this request against non-instrumented program and against instrumented program, and we measured throughput. So that's the difference in throughput. This is the throughput. That's the number of requests processed. So this 70% number is the difference in number of requests that the instrumented non-instrumented program can handle. Sure. Why not? Why meaningless? No, we had a server machine, we had a few client machines. Okay, I'd like to take this offline. So let's look at signatures. The first signature is the signature that has only 1 attack packet. So this length of packet, this is the packet that represents as regular expression, this is length constraint. So it's pretty much the same as the signature that we constructed in our example. This is the bind signature for DNS daemon. So 1 packet, that's a length. This is the length constraint. remote cat daemon has a signature that consists of 3 packets because this cat daemon requires user authentication. So here we can see user packet, password packet, the length constraint, and the length constraint for the last packet. All the signatures will generate automatically from a single attack instance. Now let's talk about the recovery. Is it really useful? The overhead is pretty high, it's 70%. Maybe we can do well without recovery. And we think that recovery is really useful because many programs are single-threaded and they are like event-driven. And if you just terminate the program, then you disconnect all the clients. So you have only one bad client, you have, let's say, a dozen of good clients. You disconnect one bad and you disconnect a dozen of good, which is very bad for good clients. And the same attack can be repeated in the future, and therefore the attacker can implement the denial of service attack if you simply terminate the program instead of recovering. If you recover it, then repair the effect of the bad guy, but you allow good guys to continue their execution. And the same trade-off exists in the case of source code analysis tools. Whenever you have a bug, if you use static code analysis tool, then you first need to find out this bug. And these tools are prone to false positives, so you need to determine whether it's a false positive or a real bug. If it turns out to be a real bug, then you have to come up with a fix. You have to upload this patch to the developer side. The developer has to verify this patch. So it's also a lengthy process, and it involves a lot of human expertise. So there is the same trade-off. You either invest a certain amount of runtime, as we do, or you invest a certain amount of developer's time, which is probably more expensive. Now we arrive at the conclusion. DIRA is the first system that solves the problems of attack detection, identification, and repair in a unified way using memory address log. It can produce accurate multi-packet signatures from a single attack instance, which we believe is a big achievement because all the previous systems either reported last attacking packet or they required a large pool of network data to generate an accurate signature, multi-packet signature. Dynamic slicing of the memory address log is the underlying technique behind our tool. And this is a well-known technique from programming languages, but I think we just found some cool applications for this programming languages technique. And we plan to apply the same technique in the future to generate patches for buffer overflow attacks. This is what we're working on. We're planning to work in the next few months. Our tool is available for download. Please visit our website and download it and play with it. So if you find bugs or if you have any experiences to share, please mail me, and I'll be happy to answer you. Thank you. I have one book, one question. Yes. I'm sorry. Well, our program generates a signature whenever an attack happens. It doesn't use history. It doesn't look for previous packets. It doesn't analyze them. So whenever you perform an attack, a signature will be generated. So the question is whether this signature will be different from previously generated signatures or not. And I think the answer is yes, because if the length is different, then the regular expressions will also be different. Yes, this is a kind of denial of service attack, but we think it's like more lightweight than complete program restart, because a complete program restart disconnects all clients, all benign clients, and recovery doesn't disconnect anybody except attacker. And therefore, the benign clients will be able to perform their requests slower than when the program runs normally, but at least they won't be disconnected. which we believe is pretty good. Memory address log is a circular buffer. Yes, the log records are used constantly, and previous records are freed up when the record is about to be used. Yes. Okay, thank you very much.